This is my part of the presentation for the SIR model for COVID-19.
So in the SIR model, we can set up what SIR stands for, how it represents this total population, and some understood information that we'll use in calculating certain things about a disease. So in the SIR model, the total population is divided into a few different components that will ultimately represent the entire population. S for susceptible, people who can catch the disease; I for infected, people who have the disease and can infect others; and R for removed, those people who have just had the virus or had it at some point such that they can no longer be infected because they're immunized, or they could be people who have died to the virus also. So we can talk a little bit more about that removed category in a moment. We've got to make some assumptions that will help us to use the model in an example that doesn't change that much, so that our predictions with the model can actually be topical in the real world. For example, the first assumption is that the epidemic doesn't last so long that the population has any noticeable change in it with respect to time. So we want to think about the total population changing as the epidemic occurs. The second assumption relates to people being infected by those who already have the disease, and those who don't, so the I and the S basically, infected and susceptibles. We're assuming here that the rate at which people interact with each other during our time period remains the same as well, which means that the more people are infected, the more susceptible people are likely to catch the disease. Which makes sense, of course, in the real world where things like herd immunity exist, or where the growth of the disease is exponential. The third assumption will then relate to the R category of people, where people are essentially removed from the group of susceptibles or infecteds because they have had the disease before, because they have died from it. And we can assume that the rate of recovery and also death is constant as well.
So here we will build some equations, some differential equations using our different variables that show how they're related to each other with respect to time. Notice that each equation is a differential equation, and those equations will spit out slopes. Here, all of our variables are differentiated with respect to time, so the solution to each differential equation will reveal how the disease is spreading at a certain time with respect to a certain group of people, like susceptibles, infected, or recovereds. So for us DDT, or DSDT rather, the rate at which the population of people who is susceptible is changing relative to time. And for this differential equation, DSDT, we can look back at our assumptions to see that number 2 will show us that the amount of people susceptible to the disease and the amount of people already infected are related, they're proportional to each other. That's I and that's S, and they're being multiplied by each other there in that equation. DSDT is the rate at which people who are susceptible is changing with respect to time. So the more people become infected, if the disease is growing, of course, the less people will be susceptible to the disease, because the more have moved from the susceptible category to the infected one. And more people become infected or immune or die to it as well. So it's equal to negative r since it's decreasing, and r is being this rate of contact. This lowercase r is this rate of contact, which refers to our assumption in number 2. And it's multiplied by, in other words, it's proportional to I, which is just the amount of people that are infected to begin with, or at a certain time rather, the amount of people that are infected. And it's also multiplied by the number of susceptible people S, since it is proportional to the amount of people who are susceptible as well. The S and the I being multiplied, being next to each other in the equation, symbolizes how they are interacting with each other, and the R represents the rate of that interaction. For the infectives, we're looking at a change that is positive, because people will grow in this category. So this is the DIDT equation. Because people will grow, essentially, this is just the exact same equation, but it's positive. And this just represents basically that people are interacting as they were for susceptibles at this constant rate R. And as they interact, the group of infectives grows over time. And since this differential equation calculates with respect to the infectives group over time, so when the infectives grow, of course, as the susceptibles diminish. We have to add one thing, though, or rather subtract one thing, that refers to assumption number 3, that infectives will recover or die at a constant rate. So we have to subtract this variable A, which represents that recovery or death rate as a constant value. And so this value is times the number of infectives. So it's only the infected people who are either recovering or dying. So that's why you have A times I on the right side. And finally, at the bottom, the removed category is just basically going to give you more details about how that right side of the equation on DIDT is behaving. Essentially, it's how those people are growing or diminishing with respect to time, of course. And this is times I, the amount of infectives. And this just makes sense because at the beginning of an outbreak, there are no infectives. So, of course, nobody will be recovered at that point. If I is 0, the recovery rate times no one will be infected. So that's how that works there. So our first question is, will the disease spread? And we can answer this using the SIR model. So a disease will spread if the value of I, the infectives, increases from its initial value of 1, or how many people had the disease initially. I not referring to the amount of infectives at time 0. So when no time has passed. If any time had passed, we could use those numbers to predict a change in the disease in the population, but at the very instant that it is first discovered. So basically, that's when will I not change? And we're answering this question, and this will take us to further questions after, and it's the rate at which people are being infected at this time 0. So there's this big bottom equation that looks kind of ridiculous, but all it is that when you substitute S naught, so the amount of susceptible people at time 0, into our equation for I, and remember that susceptible people will diminish as the infectives increase, and you can factor out an I, and what you get is this differential equation that determines if the disease will spread. So in this equation that looks kind of ridiculous, essentially it comes down to this determining factor of whether or not the disease will spread being dependent entirely on the sign of the term on the right of the differential equation. The term on the right looks complicated, but it's just the infectives times a value that will be positive if the rate at which people are getting better is less than the rate at which they are becoming infected, and negative if the rate of infection is faster than the rate of recovery and or death. This is sometimes referred to as Q, which is just a fraction representing the fraction of the population that comes in contact with the infected. Say if it's 0.5 or so, it's half of the population coming in contact with the infected.